Hi everyone, welcome to my YouTube channel. Today we will be discussing about wave packet. In the previous lecture we have discussed about the wave function of a free particle, and we have seen that the wave function is given by this equation 2, which are just the linear combination of plane waves, and we know the equation of plane waves is given by phi equals to a to the power I kx minus omega t. We know the general equation for a traveling wave is of x minus vt type. That is, the function is a kind of x minus vt dependent, where the v is the velocity of the wave and it is traveling in the x direction, positive x direction. If instead of x minus vt the function is dependent on x plus vt, then the wave will travel in the negative x direction with velocity v. So from plane wave equation phi equals to a to the power kx minus omega t, we get, after taking k out of this bracket, that x minus omega by kt. This equation represents a wave traveling in the x direction and its velocity is given by omega by k. And we know for free particle omega is h cut k square by 2m, and after putting this value we get h cut k by 2m, and h cut k is p, the momentum of the particle, and we know p is mass into velocity. V is the velocity of the particle. So from here we get the velocity of the plane wave is v by 2. So here we can see that the velocity of the wave is half the velocity of the particle it is representing. There is a paradox. Don't be surprised here, because we already have seen in the previous lecture that the plane waves don't represent physically realizable solution of Schrodinger equation. The actual wave function is the linear combination of those sinusoidal functions. This linear combination of plane waves are known as wave packets. A wave packet is the superposition of sinusoidal functions whose amplitude is modulated by gk as shown in the figure. This is a wave packet. These individual ripples are the sinusoidal waves, and the amplitude is this envelope. This amplitude is modulated by the function gk. It consists of ripples within an envelope. This is the envelope, outer part, and these individual functions are ripples. And the speed of the particle is not the speed of the ripples. The speed of the ripples are known as phase velocity, and the speed of the envelope represents the speed of the particle, which is known as group velocity. And the speed of the envelope depends upon the nature of the wave and can be greater than, less than, or equal to the speed of the individual ripples or the phase velocity. For waves on string, the group velocity is the same as the phase velocity, but in case of water it's half. That is, the group velocity is half the phase velocity. You can do an experiment by throwing a stone in the pond. You can see the individual ripples going faster than the envelope of the wave. Similarly, we will see that for a free particle, group velocity is twice as great as phase velocity. General equation for free particle wave function is this. We have already derived this in the previous lecture, the equation 5. let's assume that gk is narrowly peaked function around a point k naught. If gk is spread over a broad region instead of a peak at k naught, then different parts of the wave will have different velocity and the whole idea of group will lose its meaning. Since the integrand is negligible except in the vicinity of k naught, we can Taylor expand omega k around k naught, around the point k naught, and taking only the first term. So omega equals to omega at k naught plus d omega by dk at k naught into k minus k naught, and neglecting the other higher terms. So I am writing omega naught is omega at k naught, the value of omega at k naught, and omega naught prime is the derivative of omega with respect to k at k equals to k naught. So we get equation 6. Let's say k minus k naught equals to s. We are changing the variable. Then dk equals to ds, as k naught is constant. So psi can be written as, psi means the equation 5 we have already derived in the previous lecture. So psi can be written as, just put k equals to k naught plus s and omega equals to omega naught plus omega naught prime s, and we get equation 7. Then after rearranging, just taking out the minus omega naught t term here, and I am adding a new term e to the power I k naught omega naught prime t. You will see why I am adding this. I am adding and subtracting, so nothing changes. K naught omega naught prime t I have subtracted from here and added here, and the rest is the same. So I am taking out this first part out of the integration, and we are left with this I e to the power I k naught plus s into x minus omega naught t. So from equation 7, this equation, if we put t equals to 0, we get the wave function at t equals to 0 as 1 by root over 2 by integration g k naught plus s e to the power I k naught plus s x ds. If we compare equation 9 and 8, we can see that except from the shift from x to x minus omega naught prime t, the integrand is the same. So we can write psi xt as the phase term and psi x minus omega naught prime t 0. As the phase factor didn't affect psi square, we can say that the wave is moving with the velocity omega naught prime. As you can see that this is a function which is dependent on x and t as x minus vt. In place of v, here we have omega naught prime. So we can say that this is the velocity with which the wave packet is moving, and we call this as group velocity Vg. Vg is d omega by dk, the derivative of omega with respect to k at k equals to k0. We have already seen that individual sinusoidal waves or ripples, the plane waves or the sinusoidal waves which forms the ripples, moves with a phase velocity which is given by omega by k. In case of free particle, omega is h cut k square by 2m. So Vg is d omega by dk, and derivating it we get h cut k by m equals to h cut k is p by m. So this is v. V is the velocity of the particle, the classical velocity of the particle. So the group velocity is the same as the velocity of the particle. Now phase velocity is omega by k, so h cut k by 2m, h cut k is p by 2m, so this is v by 2. So phase velocity is half the classical velocity of the particle or half the group velocity of the particle. So the classical velocity is same as the group velocity or twice the phase velocity. Thank you for watching this video. I will see you in the next lecture. Please subscribe my channel for more exciting videos like this.